In this lecture, we shall discuss about orthogonality and Gram-Schmidt orthogonalization process. Here we shall discuss about orthogonality of vectors in an inner product space. Recall that in the previous lecture, we have generalized the distance or length concept of vectors. That is, we have defined that length of a vector and distance between two vectors. So, here in this lecture we shall discuss about that angle between vectors, or that is orthogonality. So, this orthogonality concept is motivated by the law of cosines in plane R2. So, let us see this. So, here we shall discuss about this orthogonality of vectors and this Gram-Schmidt orthogonalization process. So, this orthogonalization concept has been motivated by the law of cosines in R2. So, the law of cosines in R2 or in a plane, Euclidean plane, is given by this u minus v norm square is equal to norm of u square, that square of norm of v minus twice norm of u norm of v cos theta. Say this be equation 1. Here the vectors u and v, they are vectors in R2, u and v are vectors in R2 and theta is the angle between u and v. So, this norm we have considered with respect to the inner product in R2. So, the vectors u and v are like this, that if this is the vector u and this is the vector v, then this u minus v will be this vector, or in other words, and this angle theta is angle between u and v, or in other words, these are three sides of a triangle and this cosine law that holds for this triangle. So, this one, if we write in terms of inner product, then this one gives that a norm square of u minus b, this vector, that is equal to inner product of u minus b with itself, and right hand side is inner product of u with itself plus inner product of v with itself minus twice norm of u norm of v cos theta. So, on simplifying this, we get, on simplifying we get minus 2 times inner product of u and v, that is equal to minus 2 times norm of u norm of v cos theta, or cos theta is equal to inner product of u and v divided by norm of u times norm of v. Of course, here u and v are non-zero vectors, that u and V are non-zero vectors. So, this says that if u and v are orthogonal, that is if u and v are orthogonal or u is perpendicular to v, then we get then value of this cos theta, that is cos pi by 2 and this is equal to 0. So, this implies that right hand side this inner product of u v is equal to u and v is equal to 0, and conversely if this inner product of u and v is equal to 0, then this value of cos theta will be equal to 0 or theta is equal to pi by 2, that is u is orthogonal to v. So, this says that if u and v are orthogonal to each other, then this inner product is equal to 0 and the converse is also equal to 0. So, it says that, so on summarizing we can write this, that u inner product of u and v, that is equal to 0 if and only if u is orthogonal to v. So, motivated by this concept that one defines this orthogonality for vectors in an inner product space. So, here we shall define this orthogonality of vectors, in an inner product space. So, let us take that let V be an inner product space, then vectors u and v in this inner product space are called orthogonal if this inner product of u and v is equal to 0. We also define that orthogonality of a set of vectors. So, we say that a set S of vectors in V is called an orthogonal set, if every pair of distinct vectors, in S are orthogonal. Further, we say that a orthogonal set is orthonormal if it satisfies this condition. Further, an orthogonal set S is called orthonormal if norm of every vector is equal to 1 in this set S, if norm of V is equal to 1 for all vectors V in S. So, next we shall discuss about an orthogonal basis. So, earlier in case of a vector space we have seen a basis. So, now we shall define an orthogonal basis. So, this orthogonal basis, here we say again we consider an inner product space. So, let V be an inner product space. A set S of vectors in V is called an orthogonal basis of V if the following conditions hold. That first condition is that S is an orthogonal set. S is an orthogonal set, and second condition is that S is a basis for V, that is a set of vectors in an inner product space is an orthogonal basis if it is basis and every pair of distinct vectors in S are orthogonal. So, further we say that S is an orthonormal basis if that norm of every vector in S is equal to 1. So, further an orthogonal basis S is an orthonormal basis of V if norm of every vector is equal to 1. So, let us see few examples of orthogonal basis. So, here first example is that trivial one. The standard basis in Rn, the standard basis in Rn, that is this set that 1 0 0 0 1 0 0 and this 0 0 1, this is an orthonormal basis. This is an orthonormal basis for Rn. So, second example is like this. Here we shall see that this set consisting of vectors 1 1 minus 1 1 is an orthogonal set, is an orthogonal set in R2 with respect to the standard inner product, So, we shall see that if we change this inner product and take different one, then this vectors need not be orthogonal. So, it is of course important to say that vectors are orthogonal with respect to which basis, that with respect to which inner product, that mentioning that inner product is also important. Take this inner product of these two vectors 1 1 and minus 1 1, and this we get 1 into minus 1 plus 1 into 1, and that is equal to 0. So, this implies that these two vectors are orthogonal, but this set is not an orthonormal set. This 1 1 minus 1 1 is not an orthonormal set because that norm of this vector 1 1, that is equal to the positive square root of inner product of this vector with itself, and that is equal to square root of 2. So, next we can have another example, that is we consider a different kind of inner product in R 2. So, one checks that this mapping checks that for the vectors you say, that is x 1 x 2 and v is vector y 1 y 2 in R 2, this mapping or this function that u v defined like this: x 1 y 1 minus x 2 y 1 minus x 1 y 2 plus 4 x 2 y 2 is an inner product in R 2. So, with respect to this inner product, the above set is not an orthogonal set. With respect to this inner product, this set consisting of vectors 1 1 minus 1 1 is not an orthogonal set, because here this inner product of these two vectors is given by, here we get this 1 into minus 1 minus 1 into minus 1 minus 1 into 1 plus 4 into 1 into 1, and here one can see that its value is equal to 3, that is not equal to 0. So, therefore, these two vectors 1 1 and minus 1 1 is not an orthogonal set with respect to this inner product here we have defined. So, when we say that two vectors are orthogonal, with respect to which inner product we are saying, that is important. In some inner product, vectors may be orthogonal, but with respect to some other inner product, they may not be orthogonal. So, next we shall see another example, that fourth example. Here we consider the inner product space. Consider V be the inner product space that is consist of the set of all real valued continuous functions on this interval minus 1 1. So, here this is the set of all real valued continuous functions on this interval minus phi to pi. So, V is an inner product space with respect to the inner product, to this inner product inner product of f and g is equal to 1 upon pi integral minus pi to pi f x g x and dx. So, with respect to this inner product, we shall show that with respect to this inner product, the set of all functions, this set, that is sin n x n from 1 to up to this infinity. This is an orthonormal set. Orthonormal set. So, to check this, that this set of functions sin n x n from 1 to 3 up to infinity, this is an orthonormal set, one should prove that for this one checks that this integral, value of this integral 1 upon pi integral minus pi to pi sin n x into sin m x dx, this value is equal to 1 if n is equal to m and this is equal to 0 for n not equal to m. So, then next we shall see another important property of orthogonal vectors or a set, an orthogonal set of vectors, a set of orthogonal vectors is that they are linearly independent. So, this is an important result of this orthogonality, that every orthogonal set of non-zero vectors in an inner product space, is linearly independent, So, here this set of vectors, that consisting of orthogonal vectors, may be finite or infinite, but in any case this will be a linearly independent set. So, let us consider, let S be a finite or infinite set of non-zero. Here we are considering non-zero orthogonal vectors in the given space. Well, here we are considering non-zero orthogonal vectors. One thing can be noticed, that the vector 0 vector is orthogonal to every vector, and whenever this 0 vector belongs to a set, that set cannot be linearly independent. Therefore, here we are considering this non-zero set of vectors. Well, to prove that this S is a linearly independent set, here we consider a set of m vectors. Let V1, V2 to Vm be a set of m vectors in S. Of course, this m is less than or equal to cardinality of S, and the vectors v 1, v 2 to v m are all distinct. So, let V be this linear combination that alpha 1 v 1 plus alpha 2 v 2 plus alpha m v m, where this alpha i's they belongs to the field or their scalars. So, next for any k, k lies in between 1 to m, we can consider this inner product of v with v k, and this inner product is from the property of the inner product, we can see that this is equal to sum of this summation alpha I v I v k, inner product of v I v k, I from 1 to m. And since this v 1, v 2 to v m are orthogonal vectors, so for I not equal to k, this inner product is equal to 0. So, therefore, we get this is equal to alpha k times this inner product of v k with itself. This follows from orthogonality of the vectors v 1, v 2 to v m. So, then since v k is not equal to 0, since this v k is a non-zero vector, inner product of v k with itself, that is also not equal to 0. Therefore, we can have this value of alpha k can be written as inner product of v and v k divided by this inner product of v k with itself, or in other words, this is equal to inner product of v and v k divided by norm square of this vector v k. So, this is true for all k from 1 to m. So, therefore, if v is equal to 0, then alpha k is equal to 0 for all k from 1 to m. Hence, this S is a linearly independent set. So, here we have some consequences, some obvious consequences. That first corollary that we have is, if this set S, it is consist of say v 1, v 2 to v n, is an orthogonal basis, for this inner product space V, then it is easy to determine the coordinate of every vector in this inner product space. Then for every vector for every vector v belongs to V, the coordinates, the kth coordinate of V is given by this inner product of V with V k divided by V k norm square. That is the same thing we can write, that is, if this V is equal to say alpha 1, alpha 2 to alpha n belongs to this inner product space, then this kth coordinate alpha k is given by inner product of V and V k divided by V k norm square. So, in an inner product space, whenever we have an orthogonal basis, then the coordinates can be determined by this formula. So, then next we will have another consequence, that is corollary 2. So, this says that if we have a finite dimensional inner product space and if the dimension of the inner product space be n, then at the most how many orthogonal vectors we can have? So, the answer is obviously at the most n. So, if V is an n dimensional inner product space, n dimensional inner product space, then V can have at the most n number of orthogonal vectors. V can have at the most n number of mutually orthogonal vectors. So, this is obvious from the theorem that we have more than n mutually orthogonal vectors, then they have to be linearly independent, and that contradicts to the dimension of this vector space. Next, we will see another important result of this inner product spaces is that given any set of linearly independent vectors, we can construct orthogonal set of vectors from those given linearly independent vectors, and that process is called Gram-Schmidt orthogonalization process. So, here this method is called Gram-Schmidt orthogonalization process. So, this result we write as a theorem. So, this theorem is like this. We consider an inner product space V, let V be an inner product space, and V1, V2 to Vn be a set of linearly independent vectors, linearly independent vectors in V. Then from this set of linearly independent vectors, we can construct a set of orthogonal vectors like this. Then one can construct a set u1 u2 up to this un of orthogonal vectors from this v1 v2 vn such that for any k k lies in between 1 and n, this set of vectors u1 u2 up to uk is a basis for the span of, that is linear span of the vectors v1 v2 up to vk, or in other words these vectors u1 u2 uk, they depends on the vectors v1 v2 to vk. For this is true for any k for 1 2 to n. So, here while proving this theorem, we use this Gram-Schmidt orthogonalization process. So, we construct the vectors u1, we construct vectors u1 u2 to un in the following way. So, that we write in this stepwise. Say first step is that we consider this I is equal to say 1, and second step we take this ui is equal to say vi, and third step we increase this I is equal to I plus 1, and then we check that if I is greater than n, then stop, otherwise we shall construct the vector ui in this way. This ui is equal to vi minus summation this inner product of vi with uj divided by norm uj square multiplied by this vector uj, and j runs from 1 to I minus 1. So, we continue this process, that fifth step, then go to third step. So, continuing this process, that we can construct the vectors u1 u2 to un, and this method of construction is called Gram-Schmidt orthogonalization process. This is so called because the vectors u1 u2 to un will be an orthogonal set. So, to prove this set u1 u2 to un is an orthogonal set, first notice that these ui's are not 0. Note that this ui is not equal to 0 because Otherwise, Vi will be a linear combination of, if ui is equal to 0, then Vi can be expressed as a linear combination of vectors u1, u2 up to ui minus 1, and this ui, u1, u2 up to ui minus 1 are expressed in terms of the vectors v1, v2 to vi minus 1. So, therefore, this if ui is equal to 0, then vi will be a linear combination of vectors v1, v2 up to vi minus 1, and this is not true, because this set is a linearly independent set, v1, v2 to vi is a linearly independent set. So, this is not true, and hence each of this ui is a non-zero vector. So, next we shall check that this u1, u2, next we check that this set u1, u2 up to un is an orthogonal set. So, for this, for example, let us check this inner product u2 with u1. So, this u2 is given by v2 minus v2 inner product of v2 and u1 divided by norm u1 square multiplied by u1 and u1. So, on simplifying, we get this v inner product of v2 with u1 minus v2 inner product of v2 u1 divided by norm u1 square and inner product of u1 with itself, and this is equal to 0. So, this u1 and u2 are orthogonal. So, in general, for any positive integer, in general we can verify this. In general, for any positive integer m, less than or equal to n, and this r greater than or equal to 1, less than or equal to m, we have this inner product of u m plus 1 u r. So, this can be written as u m plus 1 can be expressed as, from this construction, it is equal to v m plus 1 minus summation inner product of v m plus 1 with u j divided by u j norm square times u j from 1 to m and inner product with u r. So, here this on simplifying we get that inner product of v m plus 1 with u r minus summation j equal to from j equal to from 1 to m v m plus 1 u j inner product of v m plus 1 u j divided by u j norm square is equal, and this inner product of u j with u r, and this will be equal to, again from orthogonality, that this set of vectors, this v, okay, this we can get, because it is true for all these lower values, we get this inner product of v m plus 1 u r and minus this v m plus 1 u r, because this we get v m plus 1 u r and this is equal to 0. So, this shows that the vectors u 1, u 2 to u n is an orthogonal set So, this is how we construct that this set u 1, u 2, u n is orthogonal. Then here we have to prove the last part of this theorem, that for any k the set next for any k with k lies from 1 to n, this u 1 u 2 to u n is a basis for this span v 1 v 2 to v k, because this u 1 u 2 to u k can be expressed as linear combination of v 1 v 2 to v k, and since this is a linear for any k, here this vectors u 1 u 2 to u k can be expressed from this construction only. Construction of u 1 u 2 to u k can be expressed as linear combination of vectors v 1 v 2 to v k, and since this is linearly independent set u 1 u 2 u k is linearly independent, we get that this set is a basis, u 1 u 2 to u k is a basis for span of these vectors v 1 v 2 to v k. So, here we can have one remark, that from a given set of linearly independent vectors, not only we can construct orthogonal set of vectors, in fact we can construct an orthonormal set of vectors. So, here from this set of vectors v 1 v 2 to v k, and orthonormal set of vectors, say W1, W2, Wk can be constructed as Wi can be taken as Ui divided by norm of Ui. So, now this norm of all these vectors W1, W2, Wk will be equal to 1 and they are also orthogonal. So, this will be an orthonormal set. So, this suggests that every finite dimensional inner product space has orthonormal basis. So, from here we get this result that every finite dimensional inner product space has an orthonormal basis. Every finite dimensional inner product space has an orthonormal basis. So, this we can construct from this Gram-Schmidt orthogonalization process, and then from this remark we can get orthonormal vectors. So, let us see one example that applying Gram-Schmidt orthogonalization process, how to construct orthogonal vectors from a given set of linearly independent vectors. So, here we consider R3 with the standard basis, with the standard inner product, and vectors be like this. Let V1 be the vector in R3 3 0 4, V2 be the vector -1 0 7 and V3 be the vector 2 9 11. So, easily one can see that V1, V2, V3 is a linearly independent set of vectors in R3. So, here we shall construct the corresponding orthogonal set of vectors U1, U2 to U3. So, applying Gram-Schmidt orthogonalization process, we first take this U1 be the vector V1. So, that is 3 0 4 and U2 will be V2 minus inner product of V2 with U1 divided by norm U1 square multiplied by U1. So, this is equal to -1 0 7 minus this inner product can be calculated and it is equal to 25 and norm of U1 square is also equal to 25 and U1 is 3 0 4. On simplifying, we get this U2 is equal to -4 0 3. Similarly, this vector U3 can be calculated from this Gram-Schmidt orthogonalization process like this. This is equal to V3 minus inner product of V3 U1 divided by norm U1 square u1 minus v3 u2, this inner product, divided by norm u2 square multiplied by u2, and this one can compute as 0 9 0, this vector. So, now this on applying this Gram-Schmidt orthogonalization process, we get this u1 u2 u3, that u1 u2 u3, that is the vectors consist of 3 0 4 and the vector minus 4 0 3 and this vector 0 9 0 is a orthogonal, this is an orthogonal set of vectors in R3 with respect to this standard inner product in R3. So, from here also one can get the corresponding orthonormal set. Further, this set that ui divided by norm of ui, I from 1 2 up to 3, this set, that is norm of u1 will be 5 3 0 4, norm of u2 is also equal to 5 and that minus 4 0 3, and this vector that 0 1 0 is the orthonormal set obtained from the vectors v1 v2 v3. So, this is how one can apply that Gram-Schmidt orthogonalization process and get a set of orthogonal vectors, and also further one can get a set of orthonormal vectors from the given set of linearly independent vectors. Also, this Gram-Schmidt orthogonalization process one can apply and test the linearly dependency or independency of vectors. Suppose the given set of vectors v1 v2 to vn are given and they are not known whether they are linearly independent, then we consider the non-zero vectors v1 v2 to vn and then apply this orthogonalization process. Then at some step we get the some ui will be equal to 0, then the set of vectors v1 v2 to vn, the given set will be linearly dependent. Otherwise, we will able to construct an orthogonal set of non-zero vectors u1 u2 to un. Okay, that is all for the lecture. Thank you.